Picture a blacksmith's forge at dusk, iron rods glowing from cherry red to brilliant white. 19th century physicists tried to pin down that glow by pure mathematics and found, to their horror, a fatal glitch. The hotter the iron, the brighter the predicted ultraviolet light. So bright, in fact, their equations foretold infinite energy. Reality plainly disagreed. The universe does not explode in blue flame every time a stove warms soup. Enter Max Planck, a softly spoken German who approached the problem as one might negotiate a truce. If the forged metal could absorb or emit energy only in fixed coins, never in fractions, the runaway vanished. Planck did not know why nature would use such strict denominations. He called it a purely formal trick, yet the trick worked perfectly, and the size of each energy coin became h times frequency. A constant now etched on every physics wall chart. The message was revolutionary. Light, and by extension, every field may appear smooth. But when you zoom far enough, you find pixels. Increase the furnace's temperature, and you do not pour a continuous syrup of energy into space. You pay out more coins per second. Each coin's value is set by color. Deep red coins are modest, violet ones are lavish, ultraviolet coins pricier still. Takeaway: nature refuses small change below a certain denomination. Energy comes in indivisible packets, and that simple rule saves the world from mathematical meltdown. A few years later, Albert Einstein eyed Planck's energy coins and saw a bolder picture. If light exchanges energy only in set amounts, perhaps the light itself arrives as discrete clicks, tiny bursts he named photons. The proof lay in a humble slab of zinc. Shine a dim red lamp on the metal and nothing happens. Turn up the brightness, and still the surface sulks. Swap the lamp for a faint violet beam, far less total power, and electrons leap free at once. The metal is not impressed by sheer intensity, cares about each photon's color, its single coin value. Red coins are too small to buy an electron's escape, but violet coins pay the fee instantly. Brightness now gains a new meaning. Flood the plate with more violet photons per second, and you free more electrons. Yet each electron still exits with the same punch. It is as though you are tossing equal value tokens faster, not enlarging the tokens themselves. This photoelectric effect does more than illuminate solar panel ads. It confirms that the electromagnetic field, smooth and continuous to the naked eye, is actually a high-speed rain of quanta. Dial the wavelength shorter, and each drop lands harder. Dial it longer, and eventually the drops become too gentle to budge even a single electron. Takeaway: light is not a continuous glow, but a barrage of photons, individual energy coins whose worth is stamped by color, not brightness, and every modern solar cell, supermarket laser, and digital camera cashes in on that cosmic currency. Tap the edge of a crystal glass and listen to its ringing tone. That shimmer is not made by the glass sliding through the air like a flute. It is the lattice of atoms itself flexing. Billions of them moving together in regimented waves. Inside every solid atom sit like beads on springs. Jiggle one, and the disturbance spreads, not as a mushy shuffle, but as crisp packets of vibration called phonons. Think of a theater stage populated by dancers linked at the wrists. A single tug sets a ripple that passes from performer to performer, yet no one leaves the stage. In the quantum script, that ripple is indivisible. The entire troupe either shares one phonon or none. Crank the energy, and you don't stretch the wave taller. You invite more phonons to join the tour. Magnetic materials host a similar cast of characters. Flip one atomic compass, and a ripple of spin flips sweeps outward. The quanta of that wave are magnons. Tiny magnetic murmurs that choreograph everything from credit card stripes to ultra-fast data storage. These quasi-particles matter because they explain the everyday. Heat in a metal rod is simply a bustling crowd of phonons. A click in a hard drive is a magnon ballet. They also hint at a deeper unity. Whether light in a vacuum or sound in a crystal, nature parcels energy in discrete packets. Fields differ, but their bookkeeping is the same. No partial coins allowed. Takeaway: even the solidity of a dining table vibrates in fixed quanta. Phonons and magnons reveal that matter itself plays a quantized melody beneath our fingertips. To grasp the next leap, imagine a placid pond at dawn. Flick the surface and concentric rings hurry away. That is a wave. But drop a steady rhythmic plunger, and you can set up a standing pattern. A persistent mound, a rhythmic bob that seems almost like an object perched on the water. In field language, a particle is just such a self-reinforcing ripple. Visualize the electron field filling all of space, as uniform and invisible as the air around you. Most of the time it dozes in perfect calm. But at a precise pulse of energy and a stable wobble appears a localized disturbance with fixed mass, charge, and spin. That wobble is an electron. Move the energy and the wobble melts back into quiet field. Electron gone without a trace. Creation and annihilation might sound dramatic, yet they happen everywhere. Strike a match. Thermal jostling spawns pairs of electrons and their antiparticles, positrons, for the briefest instant before they recombine into photons that warm your skin. Inside a PET scanner, positrons meet electrons, vanish. And their field energy re-emerges as back-to-back gamma photons the machine maps into medical images. In this view, vacuum is merely the field at rest, and matter the choreography of its excited steps. No billiard balls, no mini-planets, just ripples of differing styles. What feels like substance is a sustained vibration. What we call nothing is a stage ready to sing. Takeaway. Every particle from humble electron to elusive Higgs is a persisting wave in its own field. Proof that reality is woven not from things but from enduring patterns of motion. Switch on a humble LED torch, and a quiet marvel begins. Inside the fingertip-sized chip, electrons sit on one shelf of energy. Holes wait on another. When an electron drops to join a hole, it must shed a precise coin of energy. So out pops a photon of equally precise color. Billions of these drops each second make a steady beam, yet each leap is all or none. Dim the torch and you simply invite fewer leaps. The photons themselves never shrink. Slide your phone across a payment terminal. The glass back whispers in near-infrared photons that bounce off a tiny mirror inside and return in time to confirm identity. Every pulse is a regimented column of identical quanta, drilled by a microscopic laser. That same discipline drives fiber optic cables, where coherent photons sprint through hair-thin threads, ferrying live concert streams beneath oceans. Walk into a hospital's cancer ward, and you may meet a device called a linear accelerator. It whips electrons to near-light speed, then slams them into a metal target. The violent stop spawns a flash of high-energy photons, breath-precise quanta tuned to disrupt tumor DNA while sparing neighboring cells. Even healing, it turns out, is a negotiation with energy coins. From grocery store barcode readers to the quantum random chips, securing online banking, modern life is awash with gadgets that juggle photons, phonons, and electrons in discrete handfuls. We rarely pause to notice, but every flicker of an indicator light is a field announcing. One packet delivered, next one on the way. Takeaway. Technology thrives on the field's small change. Devices work by counting, guiding, or swapping individual quanta, never by pouring a continuous stream. Electromagnetic ripples, electron waves, phonons in crystal lattice. We've met several fields, each with its own family of quanta, but these are not isolated performers. They weave together into an intricate tapestry scientists call the Standard Model. Picture a vast quilt where every colored patch is a field, stitched to its neighbors by threads of interaction. Some stitches glow, those are the forces, while others pinch tight, giving particles mass or dictating how they decay. Within this quilt flows an invisible sea, the Higgs field. Unlike the wavering patches we've explored, the Higgs rarely flutters. Instead, it sits at a steady non-zero level everywhere, like a gentle fog. As quark and electron ripples move through that fog, they feel resistance, the origin of what we casually weigh on bathroom scales. Gluon fields bind quarks into protons, neutrino fields flit almost unnoticed through entire planets, and photon fields keep your Wi-Fi alive. Each follows the same quantum grammar, energy coins, creation dances. Annihilation bows, but each speaks with its own accent, defined by charge, spin, and symmetry. In the chapters ahead, we'll tour this quilt in earnest. How symmetry keeps some ripples massless, why others can find themselves inside atomic hearts, and how a burst in 2012 revealed the Higgs patch by shaking the entire fabric at CERN. For now, hold this image. The solidity of the world is a busy marketplace of overlapping fields, each trading quanta under rules as strict as they are elegant. Takeaway: all known matter and forces fit into a single stitched panorama of quantum fields. Next, we'll unfold that panorama square by square,